Okay, then I'm going to start. All right, so why am I even talking about neural networks in programming styles course? The reason is that the libraries for neural networks out there, like Keras and TensorFlow, have lots of interesting programming concepts. So they, in spite of all the math, interesting math and statistics that goes on in machine learning, the programming models that we are using to program these deep learning systems are quite interesting, and they seem to come out of nowhere, and they seem to be like something that the machine learning people kind of invented, but that is not the case. That's not the case. So I wanted to take a look, which is sort of what I did in the book, to take a look at an analysis of neural network programming from the point of view of programming, right, rather than from the point of view of math. So in order to do that, I'm assuming that some of you have taken some machine learning course along the way, but I'm also assuming that some of you have not. So I'm going to start from the basics and what's the most important things that you need to know in order to understand sort of the topic of the analysis, which is the programming aspects of these systems. So at the core, what these neural networks have is the set of neurons, artificial neurons, which is basically just a model. They call it neurons just because you know long history of this work being influenced by people who have studied the brain, cognitive sciences um, and other like that. So it's inspired by the concept of it's work that's inspired by biology and the concept of neurons in the brain, but what we're dealing here is with abstract mathematical concepts. That's all what we're doing here. So what we're doing in what we call an artificial neuron is just a linear combination of inputs. That's all there is to it. That's what this means here. It's just a linear, is you have a number of inputs and you just combine them all together linearly by multiply each of them by a certain weight, and at the end you get a number, and that number, before you spit it out, it goes through some sort of a function, and there are many such functions. It could be just a thresholding function. If it's less than 0.5, then this is a 0. If it's more than 0.5, then this is a 1, something like that. Or it can smooth it out. So some function that kind of shapes the output to some shape that is desired for specific purposes, right? It's not just a raw output of the linear combination. But basically at the bottom, this is all there is. So you have each neuron is doing just a very simple linear combination of inputs. And then what these neural networks are basically, by the way, these artificial neurons are called perceptrons. That was the original name that the person who started working on this back in the 40s. That was the name that they give to these linear combinators. So what are neural networks? They are just networks made of these artificial neurons, and they can be connected to each other in a number of topologies. So there are many topologies, as you can imagine. So they can be sort of fully connected, like the Hopfield network. They can be what's called deep feed forward, which is like you have the inputs on the left and the outputs on the right, and then it's just basically a flow from left to right. It could be a recurrent neural network, which is conceptually networks that have loops, so that this picture is actually not quite right. It's basically the outputs of some of these neurons can feed back to the inputs of the network, and so those are called recurrent neurons. That's conceptually, but in practice they actually are not like this. I'll talk more about that next Thursday or next week. So basically the idea is that you have these linear combinators, these units of linear combination of inputs that are connected to each other in some topology. And these topologies are very fittingly called architectures. Okay, so these are the architectures, and they are not unlike software architectures. Okay, there are lots of parallels in here. So the interesting thing about at least some of these networks, the feed-forward networks for sure, is the concept of that I already explained of data flow programming. So data flow, basically the network implements a function, right? So it's a function. It's actually a very simple function because it's like linear combinations all over, by modulated by some sort of an activation function. And the input neurons get the input, the output neurons show the output, right? And the neurons receive input from other neurons and send their outputs to neurons that they are connected to. And basically, what are the neurons? The neurons are data transformers, right? So you get the input, it goes through sort of the first layer, that input gets transformed into something else, that then it goes to the next layer, it gets transformed to something else. And so basically, it's very similar to the pipeline architectures that we have been sort of studying throughout this course, right? So it's at least the forward networks are definitely data flow programming, and those are the ones that I'm going to cover most. And another interesting thing about these networks is that there is no memory. So, and this is actually quite interesting. It's interesting for a lot of reasons, including in the field of architectures for neural networks. That a lot of work has been going around for a few years to try to bring back the concept of memory. Okay, to try to emerge the concept of memory from a model that essentially has no memory. Right, so what does that mean, having no memory? It means that you have it's a pure function. A network is a pure function. You give it an input, it spits out an output, but then that's it. The network does not remember anything, right? You give it another input, it spits out another output. It does not remember, in principle, what is it that happened before. It cannot pull, and like, for example, the computer architectures, the traditional computer architectures, where we have a memory that we can store, temporary values, and then we can retrieve them back and add them back and stuff like that. There's no such thing in these networks, right? These networks are just a pure function. There's no memory to remember what happened before. Again, as I will explain later, there's a lot of work in trying to make memory emerge, because it turns out that memory is actually quite important for certain problems. So feed-forward networks are the ones that I'm going to cover a little bit more in depth, although I will cover some of the recurrent networks too. So here are examples of feed-forward networks. They basically a data flow thing. It's a function. You give it an input, it gets out an output, and then it can have many layers. So it can have, and the inner layers are called the hidden layers. So here, on the left, we have an example of a feed-forward network with just one hidden layer. On the right, there's one with 4 hidden layers. This one has one hidden layer with just one output. So there's all sorts of network topologies, network architectures, right? For assorted problems, depending, and the architecture that you're going to choose depend on the problem that you are solving. So, and this starts already coming an interesting observation about neural networks is that so the solution to the problem that you have at hand is very much dependent on the architecture that you decide to use. So this is one thing that is kind of ties up with software engineering, that you cannot just expect to just put some generic feed-forward network like the one on the right and expect that the problem, by feeding it data and learning, and expect that it will work. No, it actually requires a substantial amount of preparation and design and experience to figure out what kind of network is the best for the problem that you have at hand. I mean, starting immediately in trying to figure out what kind of input layer and output layer it's appropriate for the data that you have at hand, because it really depends on what problem you have, whether it's a classification problem or if it's sort of a true false kind of problem, or if it's a regression problem. So there's many kinds of problems, and each kind of problem has their own preferred or actually required types of input and output layers. And then depending on the problem, there may be specific networks that are better for those problems other than other networks. So the first question, if you are going to, so this, what I said so far is sort of generic, nothing related to programming necessarily, but if you, as a programmer, software engineer, if you were tasked with designing a library that supports neural networks, right? And these are sort of graphs, directed graphs, that's what they are. What kind of data structures would you use, right? Ignore Keras, ignore TensorFlow for a moment. What kind of data structures would you use? So you could imagine that you could model each neuron as an object, because they are, conceptually, they are little objects that they know about other objects, right? So either way, there will be sort of a natural model of neurons as independent objects. Each one has pointers to other objects, so sort of object-oriented style. You end up with object graphs, right, of some sort. And not only that, but it could also capture the network changes dynamically. So you could create and delete neurons at runtime, right? So that would be super flexible, maybe with even actors and stuff. So, but that's, however, not how these things are implemented at all. Okay, so that kind of design is not part of the APIs that are out there, the popular ones that are out there. So on the way, how do they do this? So basically, there's no dynamicity, everything is static, and it's arrays all the way down. So fixed size data all the way down. There's nothing dynamically created. So you decide what's the shape of your network, what's the architecture, how many layers, how many neurons in each layer. That's a decision that is done upfront, right? And then by the way, those decisions are part of a set of decisions that's called hyperparameter tuning. So they call it hyperparameters, designing the network, what kind of network and how many layers, how many neurons in each layer, how they are connected. That's called sort of hyperparameter tuning. And it's basically the design of the solution, it's design of the architecture. So, but that is something that happens, sort of upfront, and then once you have the architecture, then everything is fixed. Nothing changes. So if you say that the middle layer has 100 neurons, then that's it. It's an array of size 100. It doesn't change. There's no dynamic allocation. Nothing changes as the program runs. So basically, neural networks are a very good example of array programming. So it's also because, as I mentioned last week, arrays have lots of advantages, because if you know that things are fixed size and you know exactly the size, there's lots of optimizations that can happen. And not only that, on top of the fact that there's arrays, if you have array programming, which is these high-level operations on arrays, then you're also freeing yourself for lots of optimizations done by, compilers and preprocessors and all sorts of other tools, right? That can compile, in this case, a network specification and compile it to the best possible way to the hardware at hand. So if it's GPUs, then it compiles it to run in GPUs. If it's CPUs, then it compiles to run. So there's all sorts of optimizations that can be done by automated, compiler-like tools, because we know exactly the sizes of things and how things connect to each other. The network is a static thing. After we decide, how it looks like, then nothing changes. So what are tensors in this world of tensor? It's called even TensorFlow. So tensors are basically now the fancy word. Actually, it's a word that comes from physics. It's not. It has not been invented by machine learning. So tensors are multidimensional arrays of numbers representing both data and functions. That's the funny thing. Another interesting thing about this world of neural networks is that, again, because they are very much functional programming, in functional programming, there's, if you remember the lambda calculus, there's no distinction between programs and data, right? Everything is a function, a lambda expression, and you can, numbers are lambda expressions, and programs are lambda expressions. Everything is a lambda expression, right? So everything is just nothing. So the same thing here. So in this world of neural networks, everything is a tensor. So the data are tensors. The transformations are also represented by tensors. Basically, the weights are tensors. The inputs are tensors, the outputs are tensors. They're basically they are multidimensional arrays of numbers represented data and data transformation functions. So that's where tensors, the word tensor is I think that an important thing is my understanding, because I looked it up in physics, how the physicists have been using this word. The reason why the word is needed rather than just, a multidimensional array, right? You could use multidimensional array. That's a generic, but the reason what makes a tensor really not just a special multidimensional array, at least in physics, is that it's an array that can have functional information, right? That transforms data that comes in, right? So it's potentially a representation of a function, not just of data that you would act, but it's actually a representation of a function. Okay, and so that's why. So basically, if you look at it here, the x's are all what we would call data, right? X's are all what we call it. The w's, which are the weights, those are the ones that you can really call a function. It's a transformation. It's the thing that multiplies the input, right? And so this is basically the function that is going on in here. So this function is also represented in an array, right? But it has the role of being a function, a transformer of the input data, and that's what the tensor is. And that was my understanding when I looked it up in the context of physics. So basically, there are arrays that represent functions. So, and then there's many of them, right? So now we have, if you have a multi-layer network, each layer represents a function a transformer function, right? Each layer transforms the input of the previous layer, and produces output that gets fed to the next layer. So there's basically tensors all around. Now, I talked to you about neural networks, and in the world of neural networks, of course, the reason why neural networks are interesting and started captivating people's attention way back in the 40s is that because they have these properties of being linear combinations of things. They also back in the 40s, people started realizing that when you have these functions, they have an interesting property, which is that given examples of input and output, okay, you can derive what the right values of these weights should be. Okay, and you see, if you read chapter whatever, the first chapter of my book on the first few chapters of part 10 of my book actually guide you through examples, very simple examples. That's pretty obvious that given an input and output pair, it's pretty obvious what the weights should be, right? So you can basically trace it backwards. So if you know, because this is just a linear function, y equals alpha of x, right, plus a or something like that, it's just a linear function. Then knowing the input, you can know the output. Of course, that's what the function is. But because it's a linear function, knowing the the output and the input, you can also find the values of the weights, right? It's just, it becomes an equation of a variable that now the variable is the weights themselves, right? It's very easy to go backwards and find out what are the weights of, what weights should be here, so that given this input, you have that output, right? So that's the interesting thing that started captivating people back in the 40s, is this tantalizing possibility that perhaps given a set, not just one input and output, but now given the idea now is that if you give it one example, it computes a certain value for these weights. And now you give it another example, and now you're going to have, people had to figure out a mechanism to compute the weights, not just for that one example, but for all the examples that it has been given so far, right? That now it remembers, that this is basically an optimization that these weights now need to honor all the input-output examples that have been seen. So these have to be the best possible weights that explain the input and output examples that have been given to train, what's called training the network. So that's the interesting thing about these networks, is the possibility of having reverse computation, right? Reverse computation meaning that we don't program the function. What we have are examples of input and output, and now the goal is to find out what the function is, right? So that's the interesting thing about these systems. It's really tantalizing. It's very, very interesting. And for certain problems whose logic kind of evades us, it has been proven that it's actually amazingly good. So having said that, let me go move on into explaining the anatomy of neural network programs. And I'm going to talk about Keras because it's a nice, very powerful, relatively simple API that you can use to access, the very super powerful underlying TensorFlow, for example, or other tensor libraries. So using Keras, the anatomy of a neural network program is actually, it's an interesting, it's very different. So the way that you program these networks is not the same that you write a program, because when you're writing a traditional program, your goal is to write the logic, right? It's to write the logic, and so that's your goal. In here, it's not to write logic because we don't know what the logic is. So what we need to do is, first of all, prepare the data. You have to have examples, right? Input, output examples of what the function that you're trying to code up. Then you need to define the network model. This is, designing the architecture of the network. It's called the model. Then once you have the network model, you say, okay, it has these many layers with these many neurons in between and stuff like that. So you have that. Then there's a step of compiling the network model along certain operational parameters. So this is the part where these compiler-like tools kick in, and having the specification of the network model. Taking that specification, it compiles it to the best possible way of laying that out on whatever computer architecture you have. So it's the compilation network, and also it has also to do with loss function, optimizers, evaluation metrics, and stuff like that. So now you compiled it, and you have a model that is laid out on that's appropriate for the hardware that you have at hand, and now you have the data, so you still don't run the program. The next thing that you need to do is to actually compute the weights of those edges, right? So that's called the training phase. So training the model using training data, or it's called also fit. Basically, this comes from statistics. So having a bunch of data, input output data, the goal now is to find out the values of each of those weights that best approximate all of that data, right, of input output that is available. So that's called training. in the API, you'll see also fit. That's the more statistical terminology. And now finally, okay, once you've trained the model, meaning that you found what would be the right weights for all of those edges of the network, then finally you have the model, right, trained. And now you can use this you have the program, right? You have the function, right? And now you can use this program to derive, to actually compute. Computing is giving an input, find out what the output is. And this input, ideally, is not on any of the inputs that the network has seen, right? So the hypothesis here is that the network is capable of abstracting beyond what all the data points that it has seen, right? So you give it a bunch of input-output examples. It found out the weights, but these weights work not just for the input-output examples that it sees, but it also work, hopefully, for the input that it hasn't seen. Okay, that's a very important thing. If you train the network and it only works well for the input and out for the inputs that you have trained it on, then that model is not very generalizable. It's not very good. So what you want, the whole kind of sauce of neural network engineering is to come up with the right architecture, and also the right data, so that it generalizes beyond the data that you trained it on. But basically, if anything, this part here is actually running the program, right? Once we have, all of this stuff up until step 5. So 1, 2, 3, 4, 1, 2, 3, 4, steps 1, 2, 3, 4 are just preparation, are just devising what the function is. And so programming in this world of neural networks feels very different because it has a lot to do with handling the data, preparing the data, cleaning the data, shaping the data to whatever shape, encoding it to whatever encoding needs to. So there's a lot of other stuff that doesn't really feel like a regular program because it's not the traditional program. It's something else entirely. We're not going to program the logic. We're just cleaning up the data that's going to infer the logic. So here's the first example. And this comes in pretty much all tutorials of Keras. This is recognition of hand written digits, right? So suppose that you want. So what's the problem here? The problem is that as input, you have a picture, a pixelated picture. In this case, for example, 28 pixels by 28 pixels. Okay. So as input, you have a 28 by 28 array. That's 512, hopefully. Yeah, 28 by 28. Oh, okay. I'm sorry. This should not be 512. This should be 784. Okay, need to fix this. Okay, but basically, you have a square, a pixelated entry with some hand-drawn number. And this is going to be transformed because, as usual, there's so typically you transform this into some sort of an array, okay? And so here's some linear representation of this picture, okay? And then here's what it looks like. So we're going to say that we're going to define here. The first thing is to define the model of the network. So there's many different kinds of types of architecture. So the most common one is the sequential, which is like the feed-forward network. It's just a sequence of layers. So we're saying that it's a sequential model. And now what in those sequential models, we add layers. Okay, so here we're adding a dense layer of 512. Right, this is the first dense layer. Okay, this 512 is actually the first hidden layer. And the activation, the input shape, here's the input shape. The input shape is a tensor of 28 by 28. Okay. this is not a 2 by 2. It's actually a linear, one dimensional tensor of the size 28 by 28. So this is the input. And the thing that we're defining here is the first hidden layer, not the input layer. It's the input layer is this one here. There's also in the API, there's actually also an input layer that you can specify. There's different ways of specifying the input. This is one of them, which means that as you define the first layer, you also say what the input shape of that layer is. And this is the activation, that function that I told you about, that after the inputs are linearly combined with the weights, it passes through some activation function. So one of them is called the ReLU, the ReLU is a function that kind of flattens things onto 0 and 1. Okay, it's a discounted sort of not a complete 0 and 1. There's a little slope between the 0 and the 1. And so this is, you add one layer, and then right. So this, I'm sorry, right? There's the ReLU shape over here. And so why this in particular? Because we want for everything that is for every negative if this is negative, we don't want it. We want a 0. Okay, so we will only let pass values that are positive. That's what this means. Okay, so only the positive outputs come out of here. The negative ones go zeroed out. All right, so and then this is the hidden layer. So this is the hidden layer, but then we need to think about the output layer. So the output of the problem is, in this case, we're trying to recognize the digits. How many digits? It's from 0 to 9. So this 10 digits. So this is a sort of a classification problem. We have 10 categories, right? So we have the 0, we have the 1, the 2, the 3, the 4, the 5, 6, 7, 8, 9. And if this one is the one that has the highest value, then it means that this is supposed to be number 0, 1, 2, right? It's a number 2. If the digit is a number 6, then 2, 3, 4, 5, 6, then this one should be the one that has the highest value. Okay, so basically what we're doing here is adding this output layer that is just a layer of exactly 10 neurons. That's the number of neurons. And the activation is what's called a softmax. Softmax means that given a set of neurons on this layer, then the output is going to be the neuron that has the maximum value. Okay, that's sort of the softmax. That's what this means. So you're already seeing. I hope that it's not my job here to try to teach you neural networks in depth, but just to give you a little flavor of what's involved in solving a problem with neural networks. Okay, and in particular, you're already. I hope I'm conveying the idea that you need the problem at hand. It relates very much so with the architecture of the network. So, for example, the fact that we have 10 output neurons here is because the problem calls for 10 different categories, right? That's what we want. If we had just, one thing here, that would be a lot harder to kind of, it would be possible also, but we would have to code the output in a completely different way, right? We would have to say that, if we just have one neuron as the output, then if the digit is 0, then maybe it's an output, the value is between 0 and 0.1. If the digit is 2, then the value is between 0.1 and 0.2. So we would have to code the output in a completely different way, okay? And I'll talk a little bit more about what that means. So, and then the other knowledge that you need to have is these activation functions, and understand when they are called for. Okay, what's the right activation function for the problem at hand? And again, there can be many. For each problem has its own activation function that should be the one that should be used. So okay, so and then so once we have so up to here, these 3 lines are the specification of the network. This is, we are creating the architecture, the network architecture. Once we have the network architecture, then it's the other step that I told you, that you compile it. So you compile the network, and this is the part where these compiler-like tools come in and generate the right code for the computer architecture that you have. And then once you compile it, then you do the fitting. So this is the training part, okay? The training part requires inputs and outputs. So the training images are the inputs, the training labels are the outputs, right? So this is again, an array of inputs, an array of outputs, and then there's a bunch of other things that you can read through the chapter of my book, explain what these guys are, but it has to do with the learning algorithms. So, but the goal here, this training phase, is to infer the weights, is what I was telling about. Giving inputs, outputs, then the magic of the math tries to find the best values of those weights of the edges for the data that is being seen here. And then finally, after all this work, we can now actually use the program, and this is called predict. This is sort of more the statistical word, but the idea is that given again an array of test images that hopefully are not exactly the same as the ones that we used for training, then giving those sets images, then we can have an array of predictions. Again, this works all on arrays, so it's not just one image. It's a set. You give it an array of images, and then you get an array of predictions too. So this is actual program, right? All of the things that we did up to here is to define the network, which is sort of design the program, and then compile it, and then find out the actual function, right? Infer the function, and then you know, run the function, use the function. That's the flow of programming in this world. Now, here's one thing that I also spent a lot of time as I was analyzing neural networks from a programming perspective, is that you know, I find it very unsettling to lose control. So basically, what we're doing here with the training phase is to just give up. We're giving up. We say we don't know what these weights should be. Let's find an algorithm that tries to optimize, you know, given the input and output, and finds the best possible weights for this input and output data. This is sort of giving up. You know, the engineering me kind of has a hard time giving up. So the interesting thing about neural networks is that they are also computers. So it could have very well been back in whatever, in 1930s, I think, when we had the paper from Turing, and we had a paper from Church, Alonzo Church, about the models of computation. I wish there had been a third paper at that time. I think that was the paper that was missing, about neural networks as computers, because it's very clear that there's a computer here, actually physical machines it's very easy to imagine. Okay, what is physical machines? They're basically nodes with edges, and each edge has a certain weight. So it's very easy to make machines like that. And you can compute, basically they can compute, right? They can compute arbitrary functions. This is really interesting. And the learning part is really, you know, it's what kind of got the attention of people in cognitive sciences. But the fact that this is a very easy to imagine computer is, for me, is even more interesting, because now, and it has lots of interesting properties. It can be it's very fast. So it's a data flow kind of program. It's super fast. It can be compressed. It can be compressed very nicely too. So there's all sorts of interesting things that you can imagine that a computer, a physical machine like that, could could give us as ideas for computation. That has nothing to do with training. We could set the weights ourselves. And in fact, what I do in some of the chapters of the book is that I set the weights myself, because I know exactly what the weights should be. At least one set of values that does the function that I think it should do. So this is kind of it. So basically, if you want to, without learning, then you define the network, the architecture, and then you set the weights manually. You basically just set the weights. There's actually APIs that you can set these weights manually, and then you do predictions. And basically, it's a very high level array programming style. That's an interesting thing. It gives you basically this layer. If you have a situation that you have a pipeline of functions that are all in array programming style, then you can do this very, very easily. Another way of thinking about these neural networks is that they are also monadic structures. And so that now that you guys have seen what monads are, let me explain why they are monadic structures. In a way, so each layer is a pure function, right? It's just a pure function. There's no side effects or no memory, nothing. There's many layers are chains of functions, okay? And when we set the network, so when we do this, okay, when we do something like this, this is equivalent to our bind, okay, to the monadic bind. Okay, we're basically adding, we're building a chain of functions. That's what we're doing here. Okay, we're binding. The add means append, so basically it's the bind. Bind this layer to the previous one. Bind this layer to the previous one. That's what's going on in here. And so much so that in the case of the normal way of writing this, when you define the model, okay, this is just a specification. It's actually not the actual model. This is just a specification. You only get the model when you say things like compile or something like that. So basically, you have promises of a function, right? You develop just the specifications of the functions, and then there's a phase that actually compiles those, so it manipulates those functions as data, right? And manipulates them and actually does the mapping to a lower level representation. So that's basically the chain is manipulated as an object. And then the predict is finally then it's really run the function on a given input. That's sort of the unwrap of monads. So neural network models are monadic structures. Okay, interestingly enough, there's another connection to things that we've talked about here in this course. All right, so what I want to talk about next is the issue of data representations, which is another big thing in neural networks, because what happens here is when you go into this world, this is as low level as it gets. Okay, and if you thought that the array programming style that you did last week was already low level, this one is even more low level. In the array programming style, in the previous exercise that we did, at least you had the arrays, the NumPy offers you arrays with strings or the arrays with, other arbitrary objects, right? It doesn't need to be just numbers. But in this world of neural networks, the inputs must be numbers, okay? There's nothing but numbers. Okay, it's just numerical data, nothing else. So basically, if you are dealing with a problem that has the inputs have other types, text or images or something like that, you, as the engineer of these programs, needs to think of a transformation that transforms the type of the input, that's higher level text or images or whatever, into numbers, because all these networks do is work on numbers, nothing else. There's no strings, there's nothing. So you have to find a mapping from whatever input type, fancy input type you have, into numbers. And the reason is that all of these functions are just linear algebra functions. That's all symbolic manipulation. I mean, let me backtrack. We know by knowing, functional programming, that everything is symbolic manipulation anyway from mathematics. But anyway, this is just a linear algebra. It means that we need numbers here, and we have multiplications and sums, and that's all we have over here. So we need to get numbers. So the types of data that these problems target are images, videos, scalar variables, even categorical types like strings, text, symbols. All of these must be converted to numbers before they are fed into the DNN. And the reason why this might be just a detail, but it's actually a very, very important detail, because the representation, so the conversion, the kind of numerical representation that you decide to use has an enormous influence on how well the learning happens or not. So certain representations are better than others for learning. Okay, so the choice of the representation is actually pretty important, and again, it comes with sort of experience. So the data is encoded as vector numbers. These encodings are important part of solving the problems in this style. So as I was saying, some encodings make the problem easy to solve, while others make the problem very difficult. And the deep neural nets can be seen as a sequence of data representation transformations. That's what they are, right? They take input in one representation and they output another representation. And the learning part is about searching for suitable representations of the data. So basically we have, imagine the digit, the handwriting digit recognition problem. So as input, we have an image, a pixelated image, right, a matrix. And as output, we have 10 things. So what's going on in here is that these layers are going to have to transform the data, the 2 by 2 data, and transform it into this other representation in the best possible way, right? So that's what is going on in here. You can look at these neural networks as data transformation, searching for representations of the data. Now, one representation that is very popular and that I use throughout the book in the examples is what's called one-hot encodings for categorical data. Okay, so this is for numbers, text, for things that are discrete. Okay, one-hot encodings are used quite a lot. They are popular and simple. However, they're very expensive, and you see why. So what is one-hot? Given n different things, you use n bits where only one is 1 and the rest are 0. Okay. So for example, if you have, for example, 26 letters of the alphabet, if you wanted to encode text, just lowercase text, just the letters, then you could say, okay, so I have inputs of size 26, and then I'm going to say that the A is this vector over here, where the first one is a 1, the B is this vector over here, where the second one is a 1, the C is this one, etc. Okay, so this is very simple. It's very good for orthogonality, because now we know, we have basically 26 dimensions, and for each different thing that we have, each different symbol that we have, only one of those dimensions is activated, not many. Okay, even though these are all real numbers, this is the best possible orthogonality between the categorical data. Unfortunately, of course, this doesn't quite scale very much, because letters of the alphabet is one thing, you only have 26. But if you're going to encode words, for example, words of the English language, then we're talking about, tens of thousands of the most popular words, or even hundreds of thousands of words in the English language. And now you have to have inputs of the size 100,000, right? And that doesn't scale very well. And so, in fact, a lot of work in natural language processing has to do with figuring out what are the best encodings for natural language, for words rather than just characters. But in any case, for some of the problem, a lot of problems that you have just a relatively small number of categories of symbols, then one-hot encoding is the best, definitely. Now you may want to, the computer scientist in me wanted to explore what would happen on the other, like binary, right? So binary encoding, which is something that we use, we represent text, characters using, for example, ASCII representation, which are 7-bit or 8-bit binary representation. So the A is something like this, the B is something like this, the C is the quote is something like this, right? So these are, just regular binary encoding, right? So you could think, okay, this is much better because it's much smaller. It can represent a much larger number of different symbols, and it's much smaller. Whereas in here we would need 26. For here we would need 8 or even less, fewer, if we just use something that's not ASCII. But for 26 we need like what? How many bits? Like 5 bits, right? We would need only 5 bits to encode 26 different symbols. So the problem with this, and I tried it, you may also want to play around with it, is that what happens when you do these kinds of encodings is now you kind of lost the orthogonality. And what happens, for example, let's take A and B. So A and B, if you would encode it like that, they actually light up. This dimension lights up for both of them, and then only this one is different. And this might say, okay, great. So A and B are close enough in the alphabet. So maybe we want these to be the same. It's relatively, but then, B and the quote, okay? The B and the quote has this one and the B have this one in common and this one different. Okay, so basically the distance between A and B and the quote is the same, but these are very different. Like the B and the quote have absolutely nothing to do with each other. The A and B, you could say, okay, they're close enough in the alphabet. Maybe it's okay that they are close enough in this representation. But no, you quickly start realizing that proximity in this space is meaningful. That's the first realization, that you have a space, in this case of 8 dimensions, in this case of 26 dimensions. So, and the way that these linear combinations work is that the proximity in this space means something. Proximity and distance in this space means something. And sometimes you want it to mean something, and sometimes you don't. So, for example, here in this, we don't want, the proximity in this space is completely meaningless, right? And so that's why. And so, if you have a representation that puts 2 symbols close by that actually have no relation with each other, then you're going to have a hard time learning whatever it is that you need to learn, because the network first needs to learn that things are not related. Okay, so that's a long story to tell that the representation actually influences a lot how well the network learns or doesn't learn, and what kinds of things it needs to learn. So again, this is one of those things that you kind of need to have experience with and realize what is going on. So basically, one-hot has less rules than ASCII. That's the rule of thumb, the intuition. The ASCII rules don't mean anything in vector space. Right? If they would mean something important for our problem, then great, this would be a good representation. But they don't mean anything. For recognizing A and B, that just doesn't mean anything that they are close together. And so it's better to use some other representation that actually makes them completely orthogonal. But you can try, actually. You can try. In fact, I don't have that exercise this week, but one of the exercises in the list is to try with binary representation. Try the same thing with binary representation. You'll find out that the network has a hard time learning. Okay. So encodings versus embeddings, this is a little bit of terminology here. So encodings, they both represent data in numerical vectors. Embeddings are encodings, Okay, it's a special kind of encoding where the proximity in the space is meaningful. Okay, so an encoding is, encoding in ASCII or encoding in whatever. The word embedding is used to denote a specific kind of encoding where the proximity is meaningful. Okay, so for example, word-to-vec embeddings place the words with similar meaning in close proximity of each other, for example. So for certain problems, it helps using embeddings to start with. So it helps using certain encodings that have meaning in space, because then the network doesn't have to learn those things. Because it's already encoded in the input itself. Okay, so I'm going to stop here. We'll cover this next lecture, but I want to switch gears and show you, start talking about the homeworks this week. So one thing to notice is there's 3 exercises. The first thing is that the due date is not Sunday, but December 9, which I think is Wednesday, maybe next week. Okay, so the deadline is December 9, which is sometime in the middle of next week. So you have a little bit more time. So and the other thing is that for this week, you cannot, I don't think you can use REPL. You can try, and I've tried to Google for how to install Keras in REPL. I didn't got very far. So if somebody figures that out, please share with the rest of us. But my guess is that you cannot do it. So what you're going to do, you have to use your own computer. And the first thing, the best hurdle to this is that you have to install Anaconda. I mean, you can install whatever you want. You can use Jupyter. The Jupyter Lab in ICS is another option that you may want to use, because they already have everything prepared for using Keras. So you can do that. Otherwise, installing Anaconda on your computer, that's what I did, and it kind of worked fine. So Anaconda is an IDE and a set of tools that package. It's a distribution of Python that has a bunch of machine learning and statistics things. So it already has comes with its own shell, and it's very easy to use. So you can follow this post to install, or find whatever other tutorial out there that can guide you through install Anaconda with the goal is to have Anaconda with Keras and TensorFlow. Okay, that's what you should be targeting. So then you need to do exercise 35.3, 36.4, and 40. So let me talk about 35.3. So 35.3 is based on 35, which is what I call dense, shallow, and under control. And so let me explain what is going on in here. All right, so for this part of the book, it's the other thing that I want to mention. I'm not solving the entire term frequency problem from end to end, because it turns out, as we've seen before, that this problem has lots of steps, right? So there's the problem of parsing the characters, and then recognizing the words, normalizing all the characters. There's lots of different problems. Each one of these problems is worth an entire model in this machine learning world. Okay, so instead of doing the entire problem, I divided the problem into its basic little sub problems. Okay, and so a bunch of these exercises are targeted on the character level operations. And then there's also a bunch of other exercises that are targeting on the word level operations. Okay. So, and I mean, I would, if somebody wants to really explore this, you can try to figure out an entire network that does the entire problem. Okay, I'll be very curious to find out if one of you is able to do that. So basically go from characters all the way to recognizing the terms and their frequencies. So that would be an interesting thing. But so these exercises are just focusing on very small little problems. So the first one, the one on 35, focus just on the characters, and what it's doing is to given a stream of characters. So given characters, the text, the characters in the book, it just normalizes them. Okay, it just does the normalization. So basically, it transforms the letters to lowercase. It eliminates all the numbers, all the punctuation. It does the step of normalization. Okay, so given a sequence of characters that are uppercase, numbers, punctuation, space, etc., the output is going to be a similar stream of numbers of characters, but where the uppercases are transformed to lower cases, where the punctuation is transformed into empty space, and the numbers are also transformed into empty space. So that's what's going on in here, just a simple transformation. So if I can start here from here to line 62. Okay, the program starts in line 62. I build the model, and I'll tell you what this is. Then I'll just print out just a summary of the model on the screen. And then I'm actually hard coding the weights. Okay, this is an example where I actually hard code. I knew exactly what the weights are going to be here. Okay, then there are many possible values, but I know exactly one. Okay, so I'm just setting them directly, and then I'm running. So basically, I'm encoding the characters. I do one hot encoding, and then I'm predicting. So this is running the function, right? That I put the weights on, and then I decode. I decode the output, right? So given a one hot encoding, I see what it is, okay? And then I print. This is going to be the character, right? Well, in this case, it's going to be a string, an array of characters. So let me explain what is going on in here. So first, let me talk about the encoding, one hot encoding and decoding. So actually, no, let me not talk about that first. Let me talk about the model first. So it's a sequential model with just one dense layer. I wonder if I have a picture here. Hold on. I don't have a picture, but it's just one. It's just one dense layer. That's all. That's all we need to solve this problem. So the input is going to be the size of the input vocabulary size, which is the length of characters. Okay, so characters in Python gives you so right. So the characters are all the printable characters of a string. Okay, this is like 100 if you run this in Python. Okay, do I have a REPL here somewhere? Hello? No, I have to import something. Import this thing. No, here. All right, so these are all the characters, printable characters, numbers, letters, lowercase, uppercase, all the punctuation and all of that stuff. Okay, so these are my input, and I think that if you do this, if you measure this, I believe this is 100. Yeah, so there's 100 different characters. Okay, so what's going on in here is that I have arrays. So the number of different symbols is going to be 100. And then I have the indices of the chars on the one hot representation. Okay, so I'm putting so each of these characters is going to have a 1 in its corresponding place. Okay, and then I have the reverse thing, which is the given. So I have the char indices meant given the char, what is its index? And then I have the reverse lookup. Given an index, what's the char? Okay, that's what's going on in here. So in any case, the input vocab size is 100. And so what I'm doing here for building the model is that I'm building a dense layer. Just I have it 100, and I'll tell you why, because it makes things very easy. And then I have an input shape of 100. So basically I have the input 100, neurons, the output is going to be another 100 Eurex. That's actually, I'm sorry, that's not even a hidden layer. That's just the input and not the output, because this problem is so simple. Okay, that's just the input layer, which is 100, and the output layer, which is 100. And then there's fully connected. So basically, there's edges that connect every input with every output. Okay. And so, and then I get a softmax activation because I want to have, of all those 100 outputs, I know that I only will have just one is going to, it's a categorical problem. So I want to know which one is the maximum, right? So that's my model. Very simple model, not even hidden layers. And everything is size 100. So if you think about it, and I explained through the book, what the right weights should be, but basically think about the letter A, for example, and let me show you. Okay, think about the letter A, capital A. All right. So the letter capital A is going to be 10, 36, like 37, something like that. It's like index maybe 36 or something. In this array, it's going to, the 1 is going to be on index 36. So now we have this fully connected. So basically, the neuron, if I have a capital A and the input as the input, right? I have 100 neurons. I'm going to have the 36th neuron that is 1, and all the others are going to be 0. So, but the function that I want at the end, the output, given a capital A, I want a lowercase a. So given that output, given that that neuron is lit up, I want to light up on the output the neuron that codes the lowercase a, which is neuron number 10 or whatever, or 11, right? Some other one over here. So I know exactly that there should be a weight of 1 be connecting these two neurons, right? There should be a weight of, and everything else should be, for this particular transformation, should be a 0. So I know that there's a 1 over there. That's what matters, right? And then what other ones? The question, the thing to solving these weights by manually is what basically start with a network where all these weights are 0, and now only some of these weights are going to be 1. And which ones are going to be 1 is the ones that enable these transformations, that move the capital A to the lowercase a, that the capital B to the lowercase b, and also that map a lot of like the numbers, all of the numbers and all of these other non-printable characters, the punctuation, all of these should map to the space character, right? All of the edges that come from these neurons should map to the space character. So basically, this is what I'm doing. I'm just setting certain edges as 1. Okay, and those are the edges that I know that it's exactly those transformations that I want. So basically here, the setting the weights, here's how I let the lowercase letters. So lowercase letters go through. So the weights from I to I for the lowercase only is a 1. Okay, those go through. The capitals go to lowercase. So basically, for all the strings in the uppercase characters, what I found the corresponding lowercase character, right? And I do this, that weight is going to be 1. And then everything else, I map it to the space. So here's the space index. And now for all the characters in printable that are not in ASCII letters, then I map those edges to 1 to the space index. Okay, that one is 1. And those are my only ones. So I have a 100 by 100 network. So I have 10,000 edges. Okay, in this network, there's 10,000 edges, and there's only a few that are going to be 1. And this is how I set up the ones. Okay, and this allows me to then do the computation. There's no learning in here. I know exactly what these weights should be. Okay, so what you're going to do in this exercise 35 is the point 3, which is All right, point 3 is another function. So implement a neural network that transforms characters into their lit counterparts. Okay, and so now you need to find a lit representation that is just one character, because two characters doesn't work. So get some, or find your own, do your own lit. So basically for ABC, so you will also have to normalize, right? So you have to basically not pay attention to capitals. Okay, so all the capital letters should map to the same, or not. Just explain. Okay, let me backtrack. In lit code, the capital letters may also map to different characters in lit. Okay, you decide, and just leave a comment. Explain what lit code you used. Okay, so that the person who's going to checks that that you did the right transformation for whatever lit code you decided to do. So this is, again, an exercise with no learning. This is something that you should program, hard code the way to yourself. So you should think about what are the edges that you have to set to 1, given the mapping that you want to do. Okay, so that's the first exercise that you can start already doing today. The second one, 36. 36 4. All right, so 36 is the same thing, but it's with learning. Okay, let me go here. If we go to 36, it's exactly the same thing, the same problem. I'm doing exactly the same problem, but now I'm doing with learning. Okay, instead of setting the weights myself, I'm letting the network learn. And so in order for the network to learn, I need a lot of examples. Okay, and now you'll see in this program now, suddenly there's a whole thing about input generation. Okay, so this is a function that generates input examples. So it generates random characters, and then it generates what are the corresponding mappings. So if it generates a capital letter, for example, then the output should be that letter in lowercase. Okay? If it generates a number 1, then the output should be a space. Okay, so I'm generating this input. It yields. Okay, it's a generator. It yields a set of inputs and the corresponding outputs, right? Input-output examples. And now I'm training the model. All right. And I'm training the model like this. And so in your case, you're going to do exercise 3.4, 36.4, which is another function, delete. Okay, so now that you decided on whatever mapping you do for lit code, then do the learning part. And I think it's going to be pretty easy. The only thing that you need to change now is the output, right? So wherever I am doing here, on line 44, that's the Buzilis, right? Line 44 is the one where you are supposed to compute the output for the given random input, and that's going to be your lit mapping over here, right? So you should do this then with the learning part. And then finally, exercise 40, I will talk about it on Thursday. That's a little more material that I haven't covered today. But starting today, you can already start working on the 35 and 36. Okay? Will there be peer review for this assignment? So yes, there will be peer review, and I'm crossing my fingers that it will work, but it may not work. I don't know. We'll see what happens. So the idea is that you're going to submit a zip file with your Python programs, just the source codes. Hopefully, everybody will be able to install Keras, and if you take somebody's program, you'll be able to run it yourself. Hopefully, that's my hope, but we'll see what happens. Keep me posted next week when we do the peer review.